Hello, this is Meteorology 113 Lecture 5, Ambient Air Pollution, Part 2. This is the second lecture of Course Module 2, Outdoor Air Pollution. This lecture will pick up from where we left off on Lecture 4. In Lecture 4, we presented a formal definition of air pollution and discussed the topic of concentrations, exposure duration, and levels of concern, and acute versus chronic health effects related to air pollution. We will now cover the basic framework in which ambient air pollution is regulated, following from these considerations. Among the subtopics to be covered are as follows. We will provide a historical perspective of air pollution regulation, which culminated in the major Clean Air Act of 1970 regulations. From this, we will introduce the topics of ambient air quality standards and criteria air pollutants. We will then summarize how Clean Air Act regulations are implemented and the national, state, and local air quality agencies involved. Past successes in controlling air quality following from these regulations and current remaining challenges will then be summarized. Turning first to the historical context. Seen here is a picture of the town of Donora, Pennsylvania on October 29, 1948. Donora, which is about 30 miles south of Pittsburgh, was among many industrial Midwest towns during this era. Donora contained many steel mills, smelters, and coal-fired power plants. The town is situated in a valley along a river, along which barges would transport raw and finished goods to and from entry ports, mills, and markets. Although one may not have guessed it, this picture was taken around noontime of this day. Stagnant high-pressure meteorological conditions were present on this day over the area, and associated with this, very weak winds and a strong temperature inversion limited dilution of air pollution emissions from the mills, smelters, and smokestacks in the town. A major air pollution episode thus occurred, which lasted several days, from October 27th through October 31st. This picture was taken at noontime on the third day of the episode. Smoke, sulfur dioxide, and other air pollutants built up in concentrations so much that visibility was reduced to the point that the day appeared as night, as one can tell by the street lights on in the foreground of the photo. 20 deaths occurred during this episode, and around 40% of the town of 14,000 inhabitants experienced respiratory problems. 50 more deaths subsequently occurred after the event ended in the month that preceded. The Donora episode focused much national attention on the increasing problem of poor air quality in the U.S., especially pertaining to these killer smog events. Air pollution regulation was highly motivated by the severity of the Donora, Pennsylvania event of 1948. Some highlights of the episode are provided here. Note that both the combination of many pollution sources, lack of regulation, and with it current-day air pollution control equipment, and unfavorable meteorological conditions for the buildup of air pollution concentrations caused the event. Another area around the country during this time that had been drawing attention related to poor air quality was Los Angeles. Rather than in Donora, where smoke and SO2 gas from factories caused an intense incident, the poor air pollution affecting Los Angeles then, and still affecting Los Angeles today, was something called photochemical smog. Photochemical smog is a mix of ozone gas and related compounds that build up on hot summer days in the presence of abundant sunlight. One can tell from the photo on the left that photochemical smog is a daytime problem. The emission sources producing photochemical smog are also a bit different than in Donora, mainly due to uncontrolled tailpipe emissions at this time from automobiles, as well as hydrocarbon gas vapors from chemicals involved in petroleum refining and various industries spreading across the Los Angeles basin associated with the post-World War II population growth of the greater LA area. Ozone pollution concentration levels were much worse during this era than today, reaching around 10 times current-day air pollution standards for ozone. As a result of the persistent air quality problems associated with photochemical smog in Los Angeles, the first air quality agencies in the country were established in Los Angeles, tasked with developing and enforcing regulations to control air pollution concentrations and emissions. Ensuing from these early air pollution problems, air pollution regulation in the U.S. culminated in the Clean Air Act of 1970, and with it the development of ambient air quality standards and criteria air pollutants. We will now cover this in more detail. Here we will itemize the major provisions of the Clean Air Act of 1970. It was established in 1970 as the first major nationwide air quality regulation. The Environmental Protection Agency was established at this time as the enforcement body for the Act, and as well for the Clean Water Act, which followed a couple years later. Among the major parts of the Clean Air Act legislation was the development of National Ambient Air Quality Standards, pronounced NAAQS as an abbreviation. These are a set of air concentration thresholds that pollution concentrations cannot exceed at monitoring stations across an area. These are similar to the levels of concern that were a topic of Lecture 4, but specifically these National Ambient Air Quality Standards are designed for regulatory purposes. The NAAQS standards apply to specific air pollutant species called criteria air pollutants. We will list the criteria air pollutants on the next slide. The NAAQS concentration standards are established based on health effects research as values that, if not exceeded, would be protective to human health for sensitive populations with adequate level of safety. NAAQS values are periodically updated as more health effects research findings become available. Alongside NAAQS, California has its own set of ambient air quality standards. So what are the specific criteria air pollutants? There are 7. First, there is ozone. We discussed stratospheric ozone in Lecture 2, where we learned that this gas has a beneficial effect when in the stratosphere in blocking ultraviolet radiation from reaching the surface. However, if ozone gas is formed at the surface, it is harmful if inhaled at sufficiently high concentrations. Ozone is a major constituent of photochemical smog shown earlier for Los Angeles. We will cover ground-level ozone air pollution in depth in a future lecture. Another of the criteria air pollutants is sulfur dioxide, which, as we mentioned in previous lectures, is connected to coal combustion. Another is nitrogen dioxide, also mentioned in previous lectures and shown in photographs as the brown gas covering cities due to the absorption of blue sunlight by this gas. Nitrogen dioxide is a portion of NOx, or NOx, and is a major part of air pollution from motor vehicles and other combustion sources. Another of the criteria air pollutants is carbon monoxide, as mentioned earlier, and a major part of motor vehicle and other combustion emissions. Then there are 2 pollutants related to particulate matter, PM10 and PM2.5. These are not specific species, but rather represent the total mass concentration of particles in the air less than certain sizes. PM10 is the total mass concentration of all particles in the air less than 10 micrometers in diameter. Likewise, PM2.5 is the total mass concentration of all particles in the air less than 2.5 micrometers in diameter. A micrometer is about 1/60th the diameter of a human hair, and thus both PM10 and PM2.5 refer to very tiny particles. Especially for PM2.5, these particles are so tiny that they can penetrate deep into lungs without being trapped in nasal and throat passages, therefore causing more serious health problems if concentrations are high enough. We will cover PM10 and PM2.5 more in future lectures. Finally, there is lead, which is a particulate metal. In terms of air pollution, lead is not as much a problem nowadays since gasoline, leaded gasoline, which was common in the 1970s and earlier, has been phased out. Lead is still an important water pollutant, however. The recent Flint, Michigan water crisis is an example of lead pollution in water that was recently in the news. The NAAQS and California air quality standards are listed here for the gaseous criteria air pollutant species. You don't have to memorize the precise values in this table, but rather familiarize yourself with the main concepts. As seen, there are two parts to a standard for a given species: the concentration level and the averaging time. For example, ozone has both a 1 hour and an 8-hour standard. The 1 hour standard in California is 90 parts per billion, and the 8-hour standard in California is 70 parts per billion, as well as the NAAQS federal standard for an 8-hour average ozone concentration is 70 parts per billion. What this means is that concentrations of ozone at monitoring stations around an area cannot exceed 90 parts per billion for any hour, or 70 parts per billion averaged over 8 hours. We will spell this out more explicitly in the next slides. Other pollutants have their own unique standards and averaging time. For example, nitrogen dioxide has both a 1 hour standard and an annual average standard. Recalling, the concept of averaging time was presented in Lecture 4 in connection with acute versus chronic health effects. The longer averaging time standards, for example the annual standard for NO2 of 53 parts per billion at the NAAQS level, is designed to guard against long-term health effects of NO2, since long-term average exposure is at issue for chronic health effects. Hourly standards, on the other hand, are more stringent standards, since they can guard against both short and long-term adverse health effects. For example, if concentrations are lower than a 1 hour standard every hour of every year, then both acute and chronic health effects are guarded against. The NAAQS and California air quality standards are listed here for the particulate criteria air pollutants PM2.5 and PM10. PM2.5 has a NAAQS annual standard of 12 micrograms per meter cubed and a daily 24-hour standard of 35 micrograms per meter cubed. PM10 has a 24-hour NAAQS standard of 150 micrograms per meter cubed and a set of California standards for both the annual and 24-hour time periods. Micrograms per meter cubed is a way of expressing mass concentration, similar to parts per million or parts per billion. In the case of PM2.5 and PM10, it refers to the mass of total particulate in the air per cubic meter, less than 2.5 and 10 micrometers respectively. The following examples make more explicit and provide further details on the application of ambient air quality standards. We first take the 1 hour California standard for ozone of 90 parts per billion. This means that the concentration of ozone measured at air quality monitoring stations across an air district averaged over 1 hour cannot exceed 90 parts per billion. Therefore, if an air district is in attainment, the ozone concentration does not exceed the standard at all monitoring stations in an area. If this is the case, an air district is in attainment of the 1 hour standard and therefore complies with the regulation. On the other hand, if ozone concentrations exceed at any monitoring station the 1 hour standard of 90 parts per billion, the Air District is in non-attainment of the 1 hour standard and is not in compliance with the Clean Air Act regulation for 1 hour ozone. The air concentrations are checked against the ambient air standards at monitoring stations across air districts, and these monitoring takes place continuously, every hour of every year. We will discuss more about air districts and monitoring stations in coming slides. We next take the 24-hour PM2.5 NAC standard of 35 micrograms per meter cubed. This means that the concentration of PM2.5 measured at air quality monitoring stations across an air district averaged over 24 hours cannot exceed 35 micrograms per cubic meter. Therefore, if PM2.5 concentration does not exceed the standard at all monitoring stations in an air district, the air district is in attainment of the 24-hour PM2.5 standards. If the PM2.5 concentrations averaged over a 24-hour period exceed at any monitoring station the ambient air quality standard of 35 micrograms per meter cubed, the air district is in non-attainment of the 24-hour PM2.5 standard. As a final example, we take the annual California NO2 standard of 30 parts per billion. The concentration of nitrogen dioxide measured at air quality monitoring stations across an air district averaged over 1 year, since this is an annual standard, cannot exceed 30 parts per billion. Therefore, if the NO2 concentrations averaged over a year does not exceed the air quality standard of 30 parts per billion at all monitoring stations, the air district is in attainment of the annual NO2 standard. Contrarily, if NO2 concentrations averaged over a year at all monitoring stations, at any monitoring station, exceeds the ambient air quality standard of 30 parts per billion for NO2 annually, the air district is in non-attainment of the annual NO2 standard. We mentioned that these standards are based on health effects research and are designed to be protective for sensitive individuals. We attempt to make this point more clear now. We will first look at SO2, specifically the 1 hour NAC standard of 75 parts per billion, and the California 24-hour standard of 40 parts per billion. First, we remind ourselves that the natural background concentration of SO2 is generally less than 1 part per billion. The ambient air standards of 75 parts per billion for 1 hour exposure and 40 parts per billion for 24-hour exposure, just mentioned, are therefore much higher than natural background air. This is because the standards refer to concentrations that would be experienced in urbanized, industrialized, or otherwise populated areas, where anthropogenic sources would exist. In terms of levels of concern for health effects, recall the slides shown in Lecture 4 for the health effects of SO2, depending on exposure duration and concentration. We can now superimpose the ambient air standards for SO2 on this plot to get an idea for the rationale behind them. Here, we roughly estimate the location on this plot of the 1 hour SO2 NAC standard of 75 parts per billion. Along the horizontal axis, we pick off 75 parts per billion, which equals 0.075 ppm. Along the vertical axis, we pick off a 1 hour exposure duration. We see the location of this point within the plot is within the blue part of the graphic. This is in the no effects portion of the graphic, with abundant margin away from the point of higher concentration along the horizontal axis, where short-term health effects associated with 1 hour exposure begin to occur, which starts at around 0.5 ppm. This highlights that the ambient air standards are low enough in concentration to be protective, aimed at sensitive populations, and designed with adequate margin away from higher concentration levels where health effects may more readily occur among the population. Note that this can also be concluded using the higher, more lenient 24-hour 1 hour standard for California of 250 parts per billion. As seen, this data point is also well within the blue portion of the plot. We can carry out the same exercise with the 24-hour California standard of 40 parts per billion. Along the horizontal axis, we pick off 40 ppb, which equals 0.04 ppm. Along the vertical axis, we pick off a 24-hour exposure duration, or 1 day. We see the location of this point is well within the blue portion of the graphic, within the no effects portion, with abundant margin away from the point of higher concentration along the horizontal axis, where health effects associated with 24-hour exposure begin to occur, beyond 0.1 ppm, or about 100 ppb. We can carry out this exercise for another pollutant, carbon monoxide, using the graphic for this pollutant shown in Lecture 4. Carbon monoxide has a 1 hour NAC standard of 35 parts per million and a 8 hour standard of 9 parts per million for both the California and NACs. We remind ourselves that the natural background concentration of carbon monoxide is generally around 100 ppb. The ambient air standards of 75 parts per million for 1 hour and 40 parts per million for 24 hours just mentioned are therefore much higher than natural background air. This is because the standards refer to concentrations that would be experienced in urbanized, industrialized, or otherwise populated areas where anthropogenic sources would exist. In terms of the health effects graphic for CO presented in Lecture 4, we plot points corresponding to the standards, the 1 hour standard of 35 parts per million and the 8 hour standard of 9 parts per million. Plotting these two ambient air standards in the chart, we get the same message. The standards are set well within the range of no symptoms with adequate margin from points of higher concentrations where health effects start to occur. Again, the ambient air standards are protective. We now discuss implementation of these standards. A basic chart of the organization of the air quality agencies tasked with enforcing the Clean Air Act and other air pollution regulations is shown here. It is the job of these agencies to manage air quality regulations across their jurisdictions. Agencies are organized from EPA, or the Environmental Protection Agency at the national level, to state agencies, and downwards to local agencies responsible for regulating their regional metropolitan areas. We particularly highlight EPA at the national level, the California Air Resources Board at the state level in California, and the various air quality management districts at the local level. The Bay Area Air Quality Management District, BAAQMD, is the local air quality management district for the San Francisco Bay Area. The South Coast Air Quality Management District is the agency responsible for regulating air quality in the Los Angeles area. There are several other air quality management districts in the state. EPA is divided into various regions across the country. California is located in EPA Region 9. California has 35 local air districts. Highlighted here in this graphic are three major ones in California where air quality can be especially poor. The Bay Area Air Quality Management District for the San Francisco Bay Area, the South Coast Air Quality Management District for the Los Angeles area, and the San Joaquin Air Quality Management District, San Joaquin Valley Air Quality Management District, which includes the cities of Bakersfield and Fresno and several others in the southern San Joaquin Valley. The Bay Area Air Quality Management District covers a 9-county jurisdiction, reaching as far south as Gilroy in southern Santa Clara Valley to as far north as Santa Rosa in Sonoma County. To check measured concentrations of criteria air pollutants against ambient air quality standards, air districts set up monitoring stations around their jurisdiction. The point of these stations is to be located to sample ambient air, representative of what the broad population is exposed to. However, since ambient air concentration levels can vary across the Air Quality Management District jurisdiction, multiple air quality monitoring stations are generally needed. Seen here by the red dots on this map are the stations operated by the Bay Area Air Quality Management District. There are many monitoring sites around the Bay Area. The local air quality monitoring station in San Jose is at 4th and Jackson Street in Japantown, close to San Jose State University. A photograph from street level looking up at the station is shown here. Jackson Street is in the foreground and its intersection with 4th Street in the background on the right side of the photograph. Atop the building, you can see various monitoring equipment that sample concentrations of criteria air pollutants, among others of interest. These measurements are taken hourly and check to see if the air quality standards are met. We now turn to the successes and current challenges of the ambient air quality regulations. We'll examine certain criteria air pollutants individually. We start with carbon monoxide, among the outdoor air pollutants highly associated with automobile emissions. Specifically, we look here at the annual trend of the 8-hour average carbon monoxide concentration across sites in the U.S. The vertical axis is concentration in parts per million. The horizontal is year, ranging from 1980 to 2005, with each tick representing an individual year. The white line tracks the average 8-hour carbon monoxide concentration averaged over all monitoring sites across the country, while the upper and lower bounds of the blue shading are the 90th and 10th percentile of the 8-hour CO concentrations across these sites. The black dashed line is the 8-hour National Ambient Air Quality Standard for carbon monoxide of 9 parts per million. Carbon monoxide was among the early success stories of the Clean Air Act. From the plot, it can be seen that by 1980, half the sites had 8-hour carbon monoxide concentrations lower than the standard, and by 1990 and after, nearly all sites had met the standard. Today, urban ambient air carbon monoxide concentrations across the country are practically always less than the ambient air quality standards. As mentioned earlier, however, this is not to imply that carbon monoxide is still something that we should not pay attention to, especially pertaining to indoor air pollution. Another traffic-related pollutant is nitrogen dioxide. This plot shows the trend over 1970 to 2017 of the highest annual average NO2 concentration among monitoring sites in the Los Angeles basin. The vertical axis is NO2 concentration in parts per billion, and the horizontal is year, going from 1970 to 2017. The red dashed line is the annual NO2 NAAQS standard of 53 parts per billion. From the plot, it can be seen that by the early 1990s, annual NO2 standards at the site with highest concentration in the LA basin became lower than the standard. Since this is a plot of the maximum annual NO2 concentration among all monitoring stations in that air district, all stations in the LA basin had therefore complied with the annual NO2 NAC standard by the early 1990s. The South Coast Air Quality Basin, which includes LA and the surrounding area, therefore went from non-attainment to attainment status for the NO2 annual standard in the early 1990s and remains so today. A main reason for the success in reducing ambient air CO and NO2 concentrations subsequent to the introduction of the Clean Air Act was the advent of the catalytic converter. This is a device, shown here on the graphic, through which automobile exhaust passes after leaving the engine block and before leaving the tailpipe. The impetus for developing the catalytic converter was the Clean Air Act, which necessitated a means for the auto industry to reduce air pollution emissions to comply with the Clean Air Act regulation. The catalytic converter is now standard equipment on all gasoline-powered automobiles since the 1970s. The passage of the exhaust through the device reduces tailpipe emissions of carbon monoxide, nitrogen oxides, and other hydrocarbon air pollutants. The catalytic converter works as follows. On the left of the diagram is an indication of the inflow of exhaust gas from the combustion chamber into the catalytic converter. On the right is the outflow of the cleaned air from the catalytic converter towards the tailpipe. The combustion gases are rich in carbon monoxide, hydrocarbon gases, and NOx. Inside the device is a honeycomb mesh of various metals, rare metals such as palladium, rhodium, as well as more standard metals such as aluminum. The exhaust gas flows through this metal mesh within the device. The metal mesh then acts to catalyze or speed up chemical reactions that convert much of the carbon monoxide in the exhaust gas to carbon dioxide, which is not harmful if inhaled, and much of the NOx in the exhaust gas to molecular nitrogen, which is also unharmful if breathed. Hydrogen in the hydrocarbon gases comes out as water vapor. As a result, much of the harmful air pollutant gases from the combustion chamber get transferred to non-health harming gases upon exit from the tailpipe. The catalytic converter is an example of how technology evolved in response to Clean Air Act regulations to improve air quality. Similar examples of technologies exist for other pollutants, which are not discussed here. While there has been much improvement with respect to many air pollutants, particularly carbon monoxide and NO2, there are still challenges going forward. This chart shows the current attainment status of air districts across the country, color-coded according to how many of the NAAQS pollutant standards non-attainment status is for. As seen, there are still several districts that have non-attainment status. California in particular can be seen to still be in non-attainment across much of the state for several air pollutants. Focusing in on California, we point out here more clearly the areas of the state and the pollutants that are in non-attainment. The left part shows the attainment status with respect to the 8-hour ozone standard. These range from marginal to extreme non-attainment. The LA area and southern San Joaquin valleys are the areas of the state in extreme non-attainment. Recall that ozone is a major part of photochemical smog, which we presented a slide in connection to LA on earlier in this lecture. There has been much improvement in controlling ozone levels over the years, but as seen here, ozone levels on bad air pollution days continue to exceed ambient air standards across much of the state. On the right, we see the other main pollutant where there's non-attainment, PM2.5. As we recall, this refers to particulate matter less than 2.5 micrometers in diameter. This is very small sized particles from smoke and other sources that can pass deeply into lungs and affect health. Again, LA and the southern San Joaquin Valley are the areas for non-attainment. This chart refers to the annual PM 2.5 standard. Other areas of the state are in non-attainment with respect to the 24-hour PM 2.5 standard. The situation in California is as in much of the rest of the U.S. The main pollutants for which non-attainment still exists are ozone and PM 2.5. The next course module will focus on these two pollutants to learn more about why these pollutants are especially challenging to control and current efforts in place to improve air quality and reach attainment with respect to ozone and PM 2.5.